Okay, good afternoon. So we're going to go up a few steps now, jump a few steps. This morning we dealt with general or very, very important building blocks, very important tools, Sigma protocols for obtaining zero knowledge and oblivious transfer. And now we're going to use those tools to construct a general protocol for two-party protocol for secure computation that will be secure, fully secure in the presence of malicious adversaries. This is much, much more difficult than the semi-honest case because parties can cheat. We saw yesterday afternoon how that's possible in theory. And what we're going to show this afternoon is how to set up a protocol in a way so that ensuring correctness, proving that the parties behave correctly, can be done in a highly efficient way. Highly efficient depends on perspective. If I run 100 meters in 20 seconds, I think that's highly efficient. Other people would not consider that. So it really depends on the context, how old you are, and your weight, etc. And it's similar here. We don't have protocols for this sort of problem that are very, very, very quick, that run in only a few seconds. But these things, we do have protocols that can run in a number of minutes or tens of minutes for, say, circuits of 40,000 gates. But as we'll see, and as I'll discuss in this talk, this specific topic has received a huge amount of attention recently, and we're really moving forward in leaps and bounds. In 2006, if I was going to give a talk on this topic, it would finish at this slide, because there were no protocols whatsoever that had a full proof of security in a malicious setting for general two-party computation that weren't GMW. And GMW isn't efficient in what we call efficient. And since then, now we have 5, 6 different protocols with a number of variations around that. And when I say 5, 6 different protocols, I mean different approaches. So it's a very, very interesting area of research. A lot is happening. And my aim in this talk is going to be a little bit different than this morning and even yesterday. I'm not going to try to give you everything about a single protocol. Rather, I'm going to try to first survey a number of techniques, and then, yes, focus on one specific approach and protocol, which happens to be mine. So, yeah, I'm biased, like I accept. But what I'll try to do, apart from the fact that I do believe that it's the best still today, but who knows, I could be wrong. What I'm going to try and do is, rather than focus on the proofs, because that's not going to really give us very much here, really to talk more about techniques and try to convince you or get over the idea of how this concept of constructing a protocol in a way that's then amenable to efficient proving of honest behavior. Okay. No? Doesn't want to do that. We can do this. All right, so as I said, in principle this has been done by GMW, but our aim today is to do it efficiently. And we saw also yesterday afternoon that BGW is more efficient than GMW, but we don't have an honest majority, so it's just not in our toolbox. It's not working. Let's try. Okay, that's what I already said. So we're going to survey known approaches and focus in detail on the cut and choose approach. And I want to start with trying to understand what's wrong with using YAO in the case of malicious adversaries. What can go wrong? Now, there are a number of obvious things, but there are also a number of more subtle things, and those subtle issues will be very, very important to understand when we try to construct our protocol. I just want to be I want to stress one very important point. You have to understand what the attacks are in order to construct a protocol that will be secure in order to prevent each attack. And when I deliver the talk, I'll say things like, this attack can't be carried out because I've done this, and this attack can't be carried out because I've done that. That is obviously not a proof of security. Even if I wrote a rigorous claim showing that certain attacks are not possible, that is not a proof of security because maybe I've missed an attack. The actual proof of security will essentially show that since these things are ruled out, I have a simulation that works. So just be aware that even if I talk in that sort of language, I don't actually mean that. Okay, so it's because of this. Okay, so we have a malicious party 1, and the first thing and the most obvious thing that a malicious party 1 can do is just to construct an incorrect circuit. Okay, so the circuit just doesn't compute the function correctly, and obviously this harms correctness. Why did I write that it harms privacy and independence of inputs? This is a test on yesterday's material. Right, you can build a circuit that reveals information about the other party's input, or reveals more information than should be revealed by the function. So it outputs, for example, the first bit of the other party's input, and this is something which is an attack through correctness, but it's an attack on privacy. What about independence of inputs?
Some relations between the inputs and continue with them.
Exactly. So you can construct a circuit which says something like, if the other party's input has this property, then compute the function with this input, and otherwise compute it with that input. And it's all a matter of how you build the circuit. The nice thing about a garbled circuit is that the party P2 has no idea what's in the circuit, so you can actually put whatever you want in there. So, you know, it's sort of like a double-edged sword. It plays against you in this case. You don't know. You can't check if P1 has constructed the circuit correctly because it's an encrypted circuit. Another thing that can actually be done, though, and this is much, much more subtle, is that P1 can carry out something called a selective input attack. What's a selective input attack? Let's think about the garbled circuit construction. Let's say we know for sure that the circuit is constructed correctly, using whatever means. Now, we know that in Yale's protocol, in addition to P1 sending the garbled circuit to P2, the parties run oblivious transfers on the inputs on P2's input with the garbled values, with P1 inputting the garbled values, and then P2 gets the correct key on each input wire. Does everyone remember that? So now think about the following very nice idea. P1, say for the first input bit that P2 has, inputs a correct key for the 0 value. Well, I wrote it here the opposite way, so I'll say the opposite way. An incorrect key for the 0 value and a correct key for the 1 value. An incorrect key will never decrypt correctly, and therefore the circuit will just not decrypt correctly, and P2 will not be able to obtain input even if it wants to, because it just simply cannot decrypt the circuit. Now let's think about what P1 can derive from this sort of an attack. If P2 obtains output, then what does P1 know? That P2's first input bit equals 1. Because P2 didn't notice any attack and just computed the entire circuit and everything was fine. But if P2 aborts because it just cannot generate output, then P1 knows that P2's first input bit is 0. This is a much, much more subtle attack, but one that is also devastating because clearly in an ideal model, it's impossible to do that. It's possible for P1 to cause P2 to abort with some probability by sending it garbage. But it's impossible in the ideal model for P1 to cause P2 to abort based on P2's input. Remember that the relaxed ideal model we talked about yesterday had this property that the adversary gets output first and then tells the trusted party whether or not to cause to have the other party get output. So it can do it based on the output, or it really depends. In this case, we can talk about the fact that only P2 gets output. If only P2 gets output, then P1 gets nothing. It has to decide whether to make P2 abort based purely on its own information and without any dependence on P2's input. So this is something you can't do in the ideal model, and it's good that you can't do it in the ideal model because this is actually a real attack that could be carried out in the real world and is very easy to do. Okay, that's what we said. So if I'm talking about a malicious... Now these are the two main problems that come up. The problem is that I'm going to introduce solutions to these problems, which will introduce additional problems, which will need additional solutions, and so on and so forth. Eventually, it converges, after, we hope, not too many iterations. So now we're doing numerical analysis. So the aim is to force the circuit constructor to behave honestly. And really this is the aim because if you remember yesterday we mentioned that in YAO, if I use the fully secure OT, then P2 can't really do anything. And the problem is just if P1 misbehaves. So that's the first aim, is just get P1 to behave correctly. When we do that, we'll introduce additional problems for P2, which we'll have to solve as well. So we can do a general zero-knowledge protocol, zero-knowledge proof. Just take the GMW compiler and apply that. That won't be efficient. So there are many, many approaches, and I'm going to actually survey the different approaches, not just to give them a name, but also just to give you an idea of what the flavor of the approach is, with the exception of 3, because Yuval is going to talk about that tomorrow afternoon. Yeah, Yuval's head went up now. So the first approach is to prove correctness of the circuit construction using zero knowledge. Now, I just said that. I said it's not efficient. No, what I said is that if I just took a general construction of a circuit and I applied a car production and did a GMW type proof, then that would not be efficient. But maybe I can construct a circuit in a very, very special way that's amenable to a highly efficient zero-knowledge proof of the fact that it's correctly constructed. The second approach is called Lego, and that is you don't prove correctness of the circuit, but you prove correctness of gates. And once you know that all the gates are corrected, these are actually solderable gates, and then you can solder them together in an efficient way, and then you get a correct circuit because the gates are correct. The third one is called virtual multi-party computation, and Yuval will talk about that a lot tomorrow afternoon. The fourth is using multiplication tuples to securely compute an arithmetic circuit. I'll talk about what that means. That's very recent work. And the last is to use cut and choose, which basically means you construct many circuits and ask this constructor to open half of them and then see whether or not they did it correctly. And that's the approach that I'm going to focus on mostly in this talk. For the case of Boolean circuits, I'm quite convinced that that's the best today. For the case of arithmetic circuits, I'm quite convinced that it's not the best today and that one of the other approaches will beat it, as long as you have an arithmetic circuit which is significantly smaller than the Boolean circuit. Okay, so again, what's this difference in Boolean and arithmetic circuits? Boolean circuits are any AND, OR, XOR, but it can basically be anything. The complexity of each gate is based on the truth table of the gate. That's what pretty much defines or is the property of the Boolean circuit approaches. An arithmetic circuit, you can add and multiply over some defined finite field, and in many cases this gives you much higher efficiency. Just to give you an example, so AES, and that's what's interesting about AES, because it's a symmetric cipher, so a symmetric cipher is obviously going to be better in a Boolean circuit, and that would be true of DES and other things, but AES actually has a very, very nice representation over GF2 to the 8. And you can actually construct an AES circuit doing over GF2 to the 8, which has only 2,400 gates, whereas AES in a Boolean circuit has about 33,000 gates. Now, this doesn't mean these are the best circuits, but these are circuits which have been constructed, and effort was made into make these circuits small, so you can see that there's a very, very big difference. But on the other hand, if I was to do DES, or other block ciphers or other functions, or in general something which needs branching and a lot of comparisons, then it would be better in a Boolean circuit. So what we're actually starting to see, and I think this is going to be apparent as time goes on and we see more and more of these protocols coming up, is that we're not going to have the best protocol for secure computation. Rather, we're going to have a number of different protocols that will all behave differently and better under different circumstances. This one might be good for small arithmetic circuits, and this one for big arithmetic circuits, and this one for small Boolean circuits, and this one for big Boolean circuits, and so on and so forth. And this one, if you have a Boolean circuit which is very wide and flat, and this circuit if it's narrow and long. And it's unfortunate, but I think that's actually what's going to happen. Okay, so let's take the first approach. The first approach is proving in zero knowledge that the circuit is constructed correctly. I'm not going to go into detail at all over these approaches. I'm just going to try and give you the flavor of what the approach is, give you a pointer for where you can read about it more. And even if the approaches, some of these approaches today don't give great results, I believe that all of the approaches have potential to be improved and give much, much better results. And this is one example of exactly that. This is a work of Jarecki and Shmatikov from Eurocrypt 2007. And they construct a Yao circuit, but rather than using symmetric encryption, which doesn't have any algebraic properties that are amenable for efficient proving, they encrypt each gate using asymmetric encryptions with a very, very nice algebraic structure, specifically Khomeini-Shoup, which is based on n residuosity, so it's a Payer type thing. You have two exponentiations mod n squared. And then they use this structure to design highly efficient zero-knowledge protocols based on sigma protocols that you use the correct keys to construct every gate, that each gate has the correct structure. So if it's an AND gate, then it should have 3 zeros and 1 1, and that will be the correct ones coming in from the input wires, and the correct ones going to the output wires, and so on and so on. And they design a whole list of different zero-knowledge protocols that you need to prove, and they put it all together, and they have the circuit constructor prove one massive zero-knowledge protocol that everything is fine. The nice thing about the paper is that the result is that you only need a constant number of exponentiations per gate. Now this is very, very impressive from a theoretical standpoint. And that's fine. I'm very happy with my theoretical hat with that. My problem is that when I want to talk about real efficiency, that O of 1 happens to be 720. Now it's 720 exponentiations that are exponentiations mod n squared, so they're large modulus exponentiations. In fact, they're even worse than large modulus exponentiations, because if you need, say, n to be at 1500 bits to get security today, you're talking about exponentiations of 3000 bit numbers. Now again, if you want a really efficient, concretely efficient protocol, then this protocol is not going to give you that. As a theoretical result that you can do over 1 exponentiation per gate, you do get that. However, I do believe that there is a lot of potential with the approach. For example, it all depends how you construct the gates and how you prove the proofs. So the fact that their proofs required 720 exponentiations per gate doesn't necessarily mean that there's something inherent, especially if you can do something that can be efficiently batched. I mentioned this morning that discrete log proofs of knowledge can be very, very efficiently batched. You can actually prove thousands of statements at the cost of only a few. This we don't know in general, but if you could construct gates that had that sort of property that you were able to batch very efficiently, and you could prove, for example, using a DDH instead of n residuosity, this would be much, much better. In general, by the way, if you can use plain DDH, plain discrete log groups, it's much, much better. They're using elliptic curve groups, you're talking about something which is 20 times faster approximately than a large modulus explanation, depends on the library. And also, by the way, if you think that every discrete log is equal, it's also not true, because if you use pairings, then you also need very, very large numbers again. So if you're looking at concrete efficiency, the type of assumption you use actually can have a very big impact on the concrete efficiency of your protocol. And 20 times is a big difference. If it takes 1 minute to run or 20 minutes to run, that's quite a difference. The second approach is Lego, and this is a result from 2 years ago at TCC. And the idea is, rather than prove that your entire circuit is built correctly, you generate many encrypted gates using something called homomorphic commitments, which are essentially a generalized name for Pedersen commitments. And what you then do is you use cut and choose on the gates in order to verify that the constructor actually generated correctly constructed gates. Once you've done that, you now have a guarantee that the majority of the rest of the remaining gates are correct, and you combine them into a fault-tolerant circuit. A fault-tolerant circuit is a circuit that can tolerate some number of incorrect gates and still correctly compute the function. And they have this homomorphic property of the commitments, enables them to actually combine gates together. If I know that these two gates are correctly constructed, then I can actually combine them together to get the structure that I want. And you, for example, can assume that your entire circuit is NAND gates, and then it's a matter of compiling only NAND gates together, although concretely that could incur additional penalties. and then you compute the circuit after that. The size of the fault-tolerant circuit, unfortunately, is S times the size of the original circuit divided by log C. So there's and where S is a statistical security parameter, and the entire protocol has an error of 2 to the minus S, so you have to set S to be about 40. So unfortunately, you incur this significant blow-up, and that's because they have a very, very naive fault-tolerant circuit. The fault-tolerant circuit basically says for every gate you have to compute, replace it with S gates, and then take the majority result of those gates. It's a very, very naive fault-tolerant circuit. If you could construct a much better fault-tolerant circuit, then you would automatically improve the complexity of Lego amazingly. The number of exponentiations per gate is 32, but unfortunately, because S equals 40, what you end up getting is 40 times 32, which is 1,280 exponentiations per gate. Now, this looks worse than the previous protocol that I showed you, but it's not for two reasons. Firstly, the exponentiations are all plain Diffie-Hellman exponentiations. And secondly, you're dividing by log C. And when you actually plug that into concretely, for example, into something like AES of 33,000 gate size, it actually turns out that this gives you better complexity, significantly better complexity than the previous protocol. But the bottleneck seems to be just the fact that you have this circuit which is so big, and if you could come up with a fault-tolerant circuit with, say, C plus S or C plus S times log C or something like that, and there are, in theory, there are theoretical results from 15, 20 years ago that do that for a different model of fault tolerance. If you could do that, then that would be amazing, and you would get a much more efficient protocol here. One thing I do want to stress, though, is we're still talking about, even if you do this in an incredibly efficient way, we're still talking about exponentiations per gate, in contrast to Yao, where the exponentiations are only for the input bits, and because you're using oblivious transfer, and from then on, each gate is computed using only symmetric cryptography, which can be more efficient. However, depending on the size of the circuit and how many symmetric operations you have to make, it's not necessarily the case that the symmetric approach will always win. So I think that these approaches are very, very important to work on and improve as well. Yeah?
Explain again what fault-tolerant circuit is and why does it need such a big security?
So the problem is that when you use cut and choose, and we'll get into that when we go into detail of the cut and choose protocol, is that all it guarantees, if I ask someone to prepare 100 somethings and I get them to open half of them and I check that they're all correctly constructed, it doesn't mean that all of the others are correctly constructed. But it does mean that the vast majority of the others are correctly constructed. Otherwise, I would have caught them with very high probability. So what I have now is I have a situation where I have many gates, of which I know that a majority of them are correct. But a minority of them may be incorrect. And now I'm using them in the circuit, and some of those incorrect gates will be used. Now, in principle, if I just took a circuit and I had even one incorrect gate, that's going to kill correctness and it won't be secure anymore. So exactly. So therefore, what I have is a circuit that tolerates some incorrect gates. In other words, it's a computation that even if some of the outputs are incorrect, it'll still be correct. How can you do that? A naive way of doing that's what they did, is to replace every gate with a large number of gates and take the majority output of each of those groups of gates. And then once you do that, you know that unless there's a majority of incorrect gates in any group, you're going to be fine. But that blows things up by a lot. So it's not an efficient way of doing it. Yes?
Is there any approach trying to use error correction coding over the results?
This is when I mentioned the results from 15, 20 years ago, I think Spielman has and other people have, they construct fault-tolerant circuits using error correcting codes that are really, really small. The blow-up is very, very minimal. But I don't know how to use that to apply that here because the model is slightly different. I think it's something which is very, very worthwhile doing. And I'm doing something I usually don't do, which is to give away nice research questions. So. The next approach is what I mentioned, the virtual MPC approach, which I said that Yuval will talk about tomorrow. And here, what they're basically doing is they want to take advantage of the fact that BGW type protocols, information theoretic type protocols are actually more efficient. And what you do is you simulate a protocol with an honest majority using dishonest majority sub-protocols for this. And I'll let Yuval talk about it. Why should I waste time? He's got 3 hours to do it. Or 1.5, sorry. The next approach is, by the way, the protocol that Yuval is going to talk about has two sides. On the theoretical side, it has a very important contribution. Concretely, efficiently, it also looks like it's something that can be very important. That's why I mentioned it here, but really Yuval will talk about it. The next one is a protocol from last year at Crypto, and if you've seen Claudio Orlandi's name a few times, you know that you have to start working quickly or he's going to come up with all the approaches before anyone else does. And here the idea is that the parties share their inputs like in BGW, add like in BGW, and multiplication, that's a problem because the real place that you need this honest majority is when you want to do multiplication. And there you can't do that without an honest majority, so the whole sharing, multiplying in small finite field approach just sort of dies. But Damgar Orlandi, in this paper, used an idea dating back to Beaver from 91 in order to actually do such a thing. And the idea is that you assume that the parties all have many tuples of the form a commitment to X, a commitment to Y, and a commitment to Z, or X equals Y times Z. By assume, I don't really mean assume. We'll have a pre-processing phase where they'll actually construct these things. But let's just forget about that for now. Pretend that they have these tuples. And in addition, they have additive shares of each of the values, meaning they have parties P1 and P2 have X1 and X2, so that X1 plus X2 equals X, Y1 plus Y2 equals Y, and Z1 plus Z2 equals Z. And in addition, the commitment is homomorphic. Homomorphic meaning that if you have a commitment to X and commitment to Y, you can compute a commitment to X plus Y. If you have a commitment to X and you have a value A, you can compute a commitment to A times X. Now, homomorphic and commitment seems, that must be difficult, but in fact it's not. Do I have a slide or do I need to do it on the wall, on the board? I'll do it on the board for a second. Just think about Pedersen's commitment. So we have commitment to X. Keep thinking that one doesn't work. Commitment to X is G to the R, H to the X. And commitment to Y is G to the S, H to the Y. So what happens if you multiply those two together? Right, these are just group values. I get G to the R plus S, H to the X plus Y. So just by multiplying them together, I actually got the addition of them. So it's homomorphic. And if I have a value A, and I do I do C to the X to the power of A, what's the commitment to X to the power of A is just G to the RA, H to the XA, which is, again, just a commitment to X times A. Not only can you do that on Pedersen commitments, you can do that also when you have additive shares of Pedersen commitments. So this is, this homomorphic commitments doesn't have to be something that's sort of scary and must be inefficient. In fact, it's not. These can be done really nicely. Now, on the first Y, let's consider a multiplication gate where we have two input Ys and one output wire. And P1, and now we have these tuples prepared on the side, okay? We already have them, we've been given them. And P1 and P2 have additive shares U1 and U2 of U, which is the value coming in on the first wire. And they have additive shares V1 and V2 of V, which is the value coming in on the second wire. This is an arithmetic circuit. We're multiplying. We want to compute U times V, or shares, additive shares of U times V. So W, let W be U times V. We want to compute W1 and W2, or have party 1 get W1 and party 2 get W2. So the W1 plus W2 equals U1 plus U2 times V1 plus V2. The problem is that party P1 has U1 and V1, and party 2 has U2 and V2, so they can't just multiply locally. That's not going to work. So how do you do it? Remember that we have these shares. Those i's should be gone there. It's x equals yz, not xi. And the first thing to do is they compute shares of u minus y. Okay, so again, they have shares of U, and they have their homomorphic, so they can compute, and they have shares of Y, so they can compute shares of U minus Y. And then they open it. Why can they open it? Oh, so I didn't mention that X, Y, and Z are random. Why can they open U minus Y? Y doesn't reveal anything? It was a bit obvious, but because Y is random. They have a additive commitment to Y, but neither of them knows Y. So opening U minus Y doesn't reveal anything whatsoever about U. Let that value be U prime. They do the same thing. They compute shares of V minus Z, and then they open that and denote that value V prime. Once again, doesn't reveal anything about V. And finally, they compute shares of U prime times V plus V times V prime times U plus a commitment to X minus a commitment to U prime times V prime. Everybody see it? No, I'm just joking. You're not supposed to see it yet. And now let's see the magic. By the way, this they can each compute because they know U prime. So this is like the A I had over here. So they can do all of this, and this obviously they can do by themselves. There's no problem whatsoever. So what does it equal to? So U prime is U minus Y. So this is U minus Y times V. V prime is V minus Z. So this is V minus Z times U. Plus Y times Z, Y times Z, because commitment to X is equal to commitment of Y times Z, right? Remember that that's the way we constructed these things. Sorry, one second. No, what did I do? Oops, what did I do? There you go. See, X equals Y times Z. So that's the way we constructed the whole thing. So that's Y times Z instead of the X, minus U prime times V prime, which is U minus Y, V minus Z. Now open it all up and you get UV minus YV plus VU minus ZU plus YZ minus UV. And you see everything cancels out. UV and UV here cancels out. YV goes here. This one stays. ZU goes out here. This is minus, this is plus. YZ is plus here and that's minus. Everything goes and we're just left with V times U. So you compute shares in this way, and then this is just local computation. By the way, all of this is just local computation, except for the opening. You need to open U prime and V prime. That's by sending each other the values. And afterwards, all you're doing is just local computation. So this is, and by the way, you can't cheat when you open your shares because we have commitments. These are Pedersen commitment type things. You can't open a different share. So once you have multiplication tuples, you can do a multiplication gate by just opening two commitments and doing a local computation. Addition is local computation. We saw that yesterday with BGW. And now multiplication is also just a couple of operations and local computation. So this is a really, really nice idea by Beaver. The problem is that you need these multiplication tuples. So what the approach in this paper is to write a specific protocol, a secure protocol for constructing, for efficiently obtaining multiplication tuples of this form. So now I have a two-party protocol where basically what I do is just generate a whole lot of multiplication tuples. I need one for each multiplication gate in the circuit. And then once I've done that, I can very, very efficiently run the entire circuit. The nice thing also about this approach is that all the time you spend constructing the multiplication tuples can be done offline before you even have the input, so you have a very natural pre-processing versus online phase. Okay? Clear? Good. Now I'll get to the approach which I'm going to spend the rest of the talk on, which is cut and choose, which is, I guess, two papers by Benny and myself, the one from 2007 and one in this upcoming TCC. And the basic idea is to have the circuit constructor prove that the Yao circuit is correctly constructed by doing the following thing. P1 will construct not one circuit but many circuits, S, and we'll say what S has to be later on. Unfortunately, S can't be 40, it has to be much more than that, and then sends them to P2. P2 then chooses a random subset of half of those circuits and asks P1 to open them. Open them, provide all of the keys on the input wires, And then P2 will decrypt the entire circuit and check that it really is a circuit computing the function. It's the circuit that they have as auxiliary input. P1 then opens those circuits. P2 checks that everything's fine. And what is guaranteed by that? So the first important thing to understand is it's not guaranteed that all of the remaining circuits are correct, but rather that just the majority of them are correctly constructed. So now I know that out of the S/2 remaining circuits, a majority of them, a vast majority of them, are correctly constructed with very, very high probability. In fact, the probability that a minority of them are incorrectly constructed is actually even less than 2 to the minus S/4. Once now we know that the circuits are correctly constructed, at least the majority of them, the parties can compute all of the remaining garbled circuits, and P2 computes all of the remaining garbled circuits, and once he does this, he can output the majority value on what he obtains. Why the majority? Because it's guaranteed that a majority of them are correct, and therefore it outputs the majority. It can't compute just one because it may be that one can be wrong with high probability. Now, what does P2 do if it obtains different outputs? So it now knows that P1 tried to cheat. It carries out the computation, and it has S/2 circuits, and it sees that there's actually more than one output. Now, this should never happen because if it's the correct circuit, the output should be the same in all of the computations. So now P2 knows that P1 is cheating. What should P2 do? This is a question for someone who doesn't know the answer yet.
Depends on his policy.
What does that mean?
He might abort or might just abort the wrong settings.
So what should he do? What's the right thing to do?
I would abort.
You would abort. Okay. Any other ideas?
Cheat back.
Hmm? Cheat back. Okay, that's difficult though, because we're going to try to stop cheating, prevent cheating.
Correct.
Take the majority and live with it.
Why?
Because if you abort, you reveal one bit of information and the other one might exploit that.
So aborting is actually a problem. Okay. Sometimes, if you're, let's say you're, take a military example, you're planning a huge attack in a certain area, and one small team of yours gets discovered and is under attack. Now, you can send all of your other forces there to save them, but if you do that, you're going to reveal to the enemy that you have actually all of your forces in the area, and your entire surprise attack is going to be foiled. And so sometimes it's actually better not to do that, even if you know that you could prevent something. It's actually going to be detrimental. So let's see what happens. If P1 detects cheating and aborts, if P2 detects that P1 is cheating and aborts, then let's think of the following attack. P1 will construct all the circuits correctly except for one. And in this incorrect circuit, it's going to say the following thing. It's going to say, if the first bit, this is my favorite example, okay? So if the first bit of P2's input is 0, then compute complete garbage. Just output a random value. And if the first bit of P2's input is 1, then compute the correct function. Now, with probability 1/2, this circuit is not going to be opened, right? Because each circuit, we're opening half the circuit. So this circuit with probability 1/2 will not be checked. If it's checked, then P2 immediately just tells P1 to go to hell. But P2, with probably 1/2, P2 doesn't open this circuit. And then it computes. Now, if the first input bit of P1 is 0, then by this policy, it's going to abort. And if the first bit of P1's input is 1, then it won't detect anything because the circuit output will be correct. So by aborting, it's actually going to reveal its first input bit. So even though you know that P1's cheating you, you actually can never let on that you actually detected that cheating. It's not going to be in your best interest. The other option is therefore just to, yes?
So how do you, so this cheating circuit is going to have a different structure, right? It's going to maybe compute F and maybe something else. So isn't that the problem?
Well,
That it has to be larger than F.
well, then you have to argue that the circuit that you have as auxiliary input is the minimum size circuit for that function. And from what I know from circuit complexity, we don't know how to do that. You want to claim that you can't make another circuit that looks the same as that and does this slightly different function. We don't know how to prove such a thing. Especially since the original circuit may have had only AND and OR and NOT gates, and now you can actually use arbitrary Boolean gates with two inputs, right? Nothing stops you from putting other things in this. You came up with another circuit which is just a little bit smaller and you're fine. So maybe people in circuit complexity do a much, much better job, then we can solve that problem, but not yet.
You can also construct stupid gates that just pass one input and you pass one input bit until the end. Because you can't look inside that gate.
Yeah, the problem is though that I said that the function it depends. It sometimes will compute the correct output or won't compute the correct output depending on something else. And he said that's a bigger function, so it should have a bigger circuit that you could detect. And I'm just saying that you can't necessarily detect it, and in many cases I assume that you actually easily can do this thing. In fact, I believe, I'm sure you can.
If the application runs a few times, then you might, if you don't vote, then you start.
No, because I'm going to output the majority value, and the majority value is going to be the correct one. So I know you tried to cheat, but because the protocol is secure against malicious adversaries, I know that the probability you actually successfully cheat is very, very small. So you're not the smartest person in the world, because why are you trying to cheat when you know you're going to fail anyway? But you're trying, and I respect that, but I'm going to ignore it. So now, what are the difficulties in attacks that are introduced by this approach? This approach is very nice, it sounds good. The problem is that underneath the carpet, I actually opened a Pandora's box of a whole lot of other attacks that are possible. So we said that I'm going to send a circuit, and then I'm going to be asked to open the circuit, and I'll open it by sending keys, and then I'll be able to check. But maybe it's possible to construct a circuit together with two completely different sets of keys. So with one set of keys, it opens a circuit correctly, and with another set of keys, it computes something completely different. Can you prove to me that that's not possible? I don't know how to do it, I admit, but it's definitely a possibility. So this can easily be solved by having P1 also commit to the keys. So it doesn't just send the garbled gates, it also sends a commitment to the input keys. And then later on, the computation will relate to the committed keys and not to just any arbitrary keys that I'll use. So rather than the P1 sending the keys on the wires, it will send decommitments to values on the wires. And rather than doing oblivious transfer on the keys, it will do oblivious transfer on decommitment values. But the commitments will be randomly ordered, so you won't know which one is the 0 one, which one is the 1 one. Okay, so that can be easily be solved, but again, this is just an example of a subtlety that most people, without getting into the details of a proof, it's very easy to miss such a thing. A much bigger problem is that of input consistency. What do I mean? We're now running the protocol on many circuits, not on one circuit. We're now running on S over 2 circuits, so it might be 80 circuits. And what's going to prevent P2 from using different inputs in each circuit? And if P2 uses different inputs in each circuit, so now again I'm relating to P2, right? I'm now enabling P2 to cheat. It will get f of x on n1 and f of x with y1, f of x with y2, and so on. It'll obtain many different outputs, and obviously we'll learn much more about x than it should. Does everybody see that? Once you compute many times, you can actually cheat more. In addition, what's stopping P1 from using many different inputs? The whole point of a garbled circuit is you don't know when you get a value whether it's related to a 0 or a 1. So in one circuit he gives a 0 value, in another circuit he gives a 1 value on the same input wire. And now P1 will obtain f of x1y, f of x2y, and so on. You might think, but yeah, P2 will then detect that different things are happening in each circuit, but it's actually not necessarily true. It depends on the function, and there are actually concrete examples where you won't detect such a thing. Okay, so These are really, really big problems. P2, the first one is actually easy to solve, and the second one adds a lot of complexity to the protocol. This is actually a big, big problem, and I'll talk about that more later. Another problem is, remember the selective input attack that I talked about, of using an incorrect value for the OT in one place? Cut and choose doesn't help with that. Cut and choose just tells you that the majority of the garbled circuits are correctly constructed. But remember that YAO has two components. You want to make sure the garbled circuit is correct, and then you do oblivious transfer on the keys. If P1 uses some incorrect values in the oblivious transfers, I'm not going to catch that at all by the cut and choose. It's completely not connected to it. That's another problem. I haven't solved at all the problem of a selective input attack. One way of solving or preventing a selective input attack is the following way, which is what we did in 2007, where we took each input bit of P2 and split it into S random inputs under the constraint that their XOR is the original bit. And then we changed the circuit so that instead of just computing the function, first it would take each set of S bits, XOR them together, and then it would compute the function based on that. Why does this help? Well, now each input bit in itself is random, and there's no correlation between each input bit and Y, except with probably 2 to the minus S. Because I took S random bits, and in order for the selective input attack to work, he has to really do this correctly on S different wires, and when it gives different, and when P1 will give incorrect keys on S different wires, it'll be caught with probably 2 to the minus S. The whole point was that it wouldn't be caught, and in this case it would be caught, and this way you can solve the problem. What's bad with this approach? Well, first it increases the size of the circuit. That I'm not so concerned about, but I'm more concerned with the fact that it increases the number of oblivious transfers. Because remember that the complexity of YAO is computing the garbled circuit and an oblivious transfer for each input wire of P2. So if S is going to equal, let's say, 40, and we have 128 input bits, then instead of having 128 oblivious transfers, I now have 5,120 oblivious transfers. Okay, that's a lot more. Okay, 5,120 oblivious transfers is a lot more than 128 oblivious transfers. You can actually use random encoding of the inputs and instead of doing this naive thing, and that improves things significantly, but it still incurs a cost, and if you have a small amount, if the input size is small, then you're going to have a large blow up and incur many more oblivious transfers. What about forcing P2 to... okay, let's get back now to input consistency, which is the main problem. We want to force P2 to use the same inputs in every circuit. This actually is easily solved because we can, instead of carrying out... Remember, in YAO we carried an oblivious transfer for each wire. Now the main observation is that in the ith wire, and I have many circuits. In the ith wire of each circuit, P2 is supposed to use the same input bit to the oblivious transfer. Because it's supposed to obtain either all the 0 keys on all of the ith wires in all of the circuits, or the 1 key in all of the ith wires in all of the circuits. So instead of doing many different oblivious transfers, it's even more efficient, just do one oblivious transfer, where the sender inputs K0 and K1i, which is the pair of, which will be a vector of all the 0 keys on the ith wire. So K0i isn't a single key, it's rather all of the keys, all of the 0 keys that are related to the ith wire in all of the circuits. And K1i is all of the 1 keys on the ith wire in all of the circuits. And P2 just obtains one of those vectors. So P2 can't use different inputs because on each wire it either gets all of the 0 keys or all of the 1 keys. Is that clear? As clear as mud, as they say? Clear? Not really. Okay, let's try the board. So I have many different circuits. Okay, I have let's say I have 3 circuits. And in these 3 circuits, we have 3 input wires for P2. Okay, so this is the first bit goes here, the second bit goes there, and the third bit goes there. I hope everyone can see. Okay, so I have 3 input bits. Now on each of these wires, there's a key, a different key. So here I would have K01, K10, K11, K20, K21, and so on. But here I'd have not K01, but K prime 01, and here I'd have K double prime 01, or 10, whatever. So that's that's the 0 keys on each of those wires. Now P2 is supposed to get the 0. Let's say Y1 equals 0. So P2 is supposed to get the 0 key for each of these 3 wires. Instead of doing 3 oblivious transfers and telling P2 to input 0 on each of those, I'll do 1 oblivious transfer where P1 will input all of these keys in its oblivious transfer. For the 0 value of the oblivious transfer, it'll do K10, K10 prime, K10 double prime. And for the 1 value, it'll do K11, K11 prime, K11 double prime. So the sender's input will be 3 keys and 3 keys. 3 0 keys versus 3 1 keys. The receiver's input will just be its bit, which is 0, 1. If it has 0, then it'll get the 3 0 keys. If it has 1, it'll get the 3 1 keys. And the result is that it can only use a single input in all of the circuits, because it can't choose a 0 value here and a 1 value here on that wire. For every wire, there's a single bit that P2 has to choose, and it can't play around with that at all. Is that clear now? Good. That justifies bringing the board, so I'm glad. Next. What about P1? P1 is where the headache starts. We want to force P1 to use the same inputs in every circuit. One approach is, again, is to use zero knowledge. Let P1 commit, well, P1 is committed to all the input values, we said that beforehand. Let P1 now prove that all of the keys that it's used are actually in each, for a given wire, when it gives you S over 2 keys, they're all associated with either the 0 bit or the 1 bit. That looks to be very expensive. It requires exponentiations. Exponentiations are expensive. You don't want to do that. At least in 2007, you don't want to do that. In 2011, you actually do want to do that, and I'll talk about that later. That's one big lesson exactly between 4 years ago and today. But again, I'll expand on it later. So instead, what we're going to do is use cut and choose on commitments. And we're going to construct, if anyone's seen the paper, a really horrible matrix of a huge amount of commitments that you can open in all different directions, and you can open it this way and that way and that way, and then you're going to, on the circuits that are opened, you're going to be opening these ones, and the circuits that are evaluated, you're going to open here, but only not there, and it's, on the one hand, it's complicated. On the other hand, the nice thing about it is it's all commitments, it's all symmetric operations. So the concept is that symmetric, in general, the concept, at least our understanding then, was that symmetric operations are much, much cheaper than asymmetric operations. So exponentiations should be avoided if you can, and cheap symmetric operations are much, much better to do. And so that's exactly what we did. The problem is that the cost was that we had 2s squared times L commitments, where S is the security parameter, the statistical security parameter. L is the number of input bits, and 2 is 2. And if you took S, all the notation is important. Now, if S is 160, which is what we actually needed for this paper, you ended up getting only 6,553,600 commitments. Each commitment is, say, I don't know, using SHA-1 160 bits, using SHA-2 256 bits. And in addition to a lot of computation, you also actually have to send about a gigabit of data. That's if 160 bit, each commitment is just 160 bits. So it's a heuristic commitment based on SHA-1, and you have to send a gigabit of data and process that. It's not that pretty, and this was a mistake. It's an important lesson, and that's why, how did we learn that it was a mistake? Anyone have any idea how we learned it was a mistake? Sorry? somebody implemented it. And it turned out that we were so worried about doing many oblivious transfers or exponentiations or asymmetric computations that we said, yeah, just do everything symmetric. It doesn't cost anything. And then you just see this huge amount of bandwidth, massive messages being sent, a lot of computation, a lot of stuff in memory, and that actually turned out to be the bottleneck of the protocol. So this was a mistake, and one has to balance. They're apples and oranges, symmetric and asymmetric operations, but you can't put everything in one basket and say, yeah, symmetric is free, let's do lots of symmetric and forget about asymmetric because that has to be more expensive. In this case, anyway, it was a mistake. Who knows, if we could have done this with S times L commitments, then maybe that would have been fine. But 2S squared times L is just ridiculous. Another problem we had in the 2007 paper, and again, I'm talking about this simply because these are important lessons that we learned from the last few years, and I think it's instructive to give that over to other people who want to construct secure protocols. There's an issue of how tight your security reduction is, or what error you get. What's the probability of cheating? And why is the probability of cheating important? If you're doing asymptotics, then no one really cares. It's negligible, so it's n to the log. The probability you can cheat is 1 over n to the log star n. That's negligible. We're done. The problem is that you need to take an n, which is 3,500 billion, and that makes things a little bit difficult. So you have to actually, if you want concrete efficiency, and I want to stress there's a bit, I'm very interested in also theoretical efficiency. So constant round protocols, sublinear protocols. It's a completely different world. If you're interested in concrete efficiency, then the tightness of your security reduction is very, very important. And we actually proved on this protocol that the probability of cheating is 2 to the minus s over 17. That's what we succeeded in proving. Now we actually, I'll talk about what we conjectured later on, but that means that in order to get an error of 2 to the minus 40, I actually need to take s to be 680. Now, that affects a number of things. Also these circuits that also these commitments that we constructed, but also the number of circuits that have to be sent. Remember, a circuit of 33,000 gates means to construct each gate is 4 ciphertexts. So now that's 132,000 ciphertexts. Each one requires 2 encryptions. So when I say 132,000, that's 264,000 encryptions. Doing that 100 times is, I've lost already, 1,600,000 or so, I think. What did I say? And doing that 600 times is 7 or 8 million. There's a difference between doing 1 million encryptions and doing 7 or 8 million encryptions. And this is a very, very important point. It also means that the commitment sets wouldn't be 1 gigabit if you actually use the security parameter to be 20 gigabits. And we actually conjectured that the error is really 2 to the minus s over 4, although I have to admit that we didn't prove it. And today I'm not even as convinced as I was once. So for concrete efficiency, coming up with a tight analysis is crucial. And sometimes you actually even introduce things into the protocol. I may be interested in working harder in order to reduce my error, my statistical error, so that I can send less circuits, because that may be the bottleneck. I actually mentioned this slide. So there's a difference between the theoretical and concrete. Both are very important, both are very interesting, but if you want to be concrete, then you have to look at things in a different way. Being negligible. Also, what we do in not just us, but all of these papers, you have 2 different security parameters. You have a computational security parameter which will tell you how big your discrete log group has to be, or how large your RSA keys have to be. And that's something which is completely separate from a statistical security parameter where you're saying that the probability of cheating and not being detected is 2 to the minus s over something. Then there are 2 very, very different parameters, and that tells you okay, so how big my encryption keys need to be on the one hand, but also how many circuits do I have to send, and how many do I have to check, and so on and so forth. So in reality, it turned out that we completely missed the point in 2007, or we didn't miss the point, but we did something which is less efficient than we could have because we were afraid of doing exponentiations and doing zero knowledge. It's not completely fair, because in 2007 we also ended up with a protocol that was relied only on general assumptions and didn't need to assume anything specific, which was an advantage. But in terms of efficiency, that was it turned out that we were wrong, and the oblivious transfers take almost no time compared to the rest. So in 2011, when we came along and said that, or in 2010, because we didn't have time yet in 2011, we came along and said that maybe we can trade things off in a more productive way, and maybe we can construct a protocol that will have more exponentiations, but will enable us to prove consistency without all of these commitment sets. And so we have more oblivious transfers and more exponentiations, but we have no commitment sets, and we also managed to get rid of the selective input attack completely for free, which is nice. In addition, we worked very hard to come up with a really, really tight analysis of the error, and we got 2 to the minus 0.31 s. Why is that important? Because that means that for that's a typo. It means it suffices to take 128 circuits. S equals 128 for 2 to the minus 40 error. Okay, so there I said it. This is obviously a typo. It suffices to take S equals 128 for 2 to the minus 40 error. Okay, and again, if I had 2 to the minus S over 4 error, which is a very easy bound to get in this protocol, then I would need 160 circuits. But the difference between 160 and 128, if a circuit is tens of thousands, is significant. It's, I don't know, 20%? No idea. So many less circuits, there are less circuits, and this is very, very important. In addition, we don't have 2 to the minus S over 17 or anything like that. This is a proven bound. So how do we prove consistency? And this I want to show you in detail. Instead of choosing in Yao, what we do is we just choose random keys on every wire. And something I've been mentioning yesterday and today over and over again is that efficiency has a lot to do with not just I'm given something, now prove it, but setting things up so that what I get is amenable to efficient proving. And so rather than just choosing random values on the wires, on the input wires, I'm going to choose the values in a very, very special way. So I'm going to take values R1 to Rs. That will be 1 for each circuit. And we have S circuits. So R1 will be associated with the first circuit, R2 with the second circuit, and so on. And I'm also going to take random values AI0 and AI1, which will be 2 random values associated with the ith bit of P1's input, but in all the circuits. And then the keys for the wire which is associated with the ith input bit of P1 in the jth circuit will be G, this is a discrete Diffie-Hellman group, G to the A1 0 times R, G to the AI 0 times Rj, G to the AI1 times Rj. Okay, so if you think about it, on the ith wire, in all the circuits, it'll be G to the AI0 R1, G to the AI0 R2, and so on, and G AI1 R1, G AI1 R2, and so on. These all look completely random. Why do they look like completely random group elements? Even if I gave you G to the, oh, maybe it's here. Even if I give you all of these values, I give you G to the R1 through G to the Rs, and I give you G to the A11, G to the A10 through G to the L1 and 0, which is for the L different input bits, all of these values look pseudo-random, look like random group elements, even given all of this. Why is that the case? No, not because A is random. A is, once I give you G to the A, it's not random at all, it's committed. DDH, the decisional Diffie-Hellman assumption, says that when you have tuples of G to the A, G to the B, G to the AB, G to the AB looks completely random, even though you have G to the A and G to the B. So even though I give you this and this still looks completely random. What's more interesting here is that I give you here 2L plus S values, and I commit essentially to 2L times S keys. Okay? There are 2L plus S values here, and they are a commitment to 2L times S keys. Because on every, there are L wires, there are 2L values, because there are 2 values on each wire. And in S circuits, there are 2 times L times S different keys. Now, what I want to do is I want to prove that when I've given you these values, and now P1 is supposed to, in the protocol, in Yah's protocol, P1 is supposed to give the keys associated with its own input. But P1 needs to prove that it gave you, for every wire, it gave you the same value, either all 0 values or all 1 values on that wire. So it means that P1 either gave you G to the A10 R1, G to the A10 R2, G to the A10 R3, or G to the A11 R1, G to the AR1 R2, and so on and so on. So the A part on every wire, the A part is going to be the same in all S wires that it gives you, or S over 2, because we opened half of them. Okay, so the only thing that's changing is the R1 through RS, but for any given wire, the A component in the exponent will be the same in all of the wires, in all of the circuits for that given wire. Is that clear? So that's what we want the prover to prove. It starts sounding like Diffie-Hellman tuple. It's sounding good. Okay, so we have these commitments. These are commitments to all of the keys. And we have S keys. Actually, it's S over 2 keys because you're only proving for half, but let's just do S for simplicity, and because I've already made the mistake in the slide. So we have these S keys, and what we want to do is we want to prove that there exists a single bit B, either 0 or 1, so that KI1 is G to the AIB R1, KI2 is G to the AIB R2, KIS is G to the AIS R2. Okay, again, the A component is AIB, AIB, and the only thing that's different is the R part. In other words, the key which is used is the same in all of them. It looks complicated, but this is just an OR between 2 what I call extended Diffie-Hellman tuples. Think about the fact that this is the case is just looking at, if I took just GA11, then taking this and multiplying all of these with GA11 is exactly what a Diffie-Hellman tuple is. Except instead of having G to the A, G to the B, G to the AB, I have G to the A, G to the AB. So I have G to the A, G to the B, G to the C, and now I have G to the RA, G to the RB, G to the RC. But that's exactly the same as a Diffie-Hellman tuple, but just longer, just extended. It's an extended Diffie-Hellman tuple. And you can actually prove it in exactly the same way as you prove Diffie-Hellman tuples. And it's an OR. Why is it an OR? Because I'm either using the 0 key or I'm using the 1 key. So I have a sigma protocol, an efficient sigma protocol for doing Diffie-Hellman tuples. It's essentially the same protocol for doing these extended Diffie-Hellman tuples, not much more expensive. And now I do the OR between the 2 of them. How do I do that? We were here this morning, so we know that using a sigma protocol I can automatically compile that together easily. It's just the OR of 2 statements. Once I've done that, I can now apply the zero knowledge proof of knowledge or the zero knowledge compilation of that for additional few exponentiations, and I'm done. And it turns out that I can do this entire really complicated proof in S plus 18 exponentiations. Which if S is like 128, which is what we said, so we're talking about 140 or so exponentiations. And it looks like a very, very complicated type of thing we're doing. We have a whole lot of wires, we have a whole lot of commitments, we want to prove consistency. If you set things up right, then you can actually do it very, very efficiently. And this turns out to be much, much, much more efficient than 6.5 million symmetric commitments. Another problem that we address, and that I mentioned that we address, is the problem of the selective input attack. And the reason why a selective input attack is possible is because we deal with different problems in a different way. Okay, so we're worried that the thief is going to come through the door, so we put a strong door and lock. We're worried that the thief is going to come through the window, so we put bars on the window. If we would put an alarm in the entire house, then apart from the false alarms, which would annoy us every night, we'd have one solution to all the problems. And sometimes, in this case at least, it turned out that if you can have one solution to all the problems, if you can combine the solution together, then you can actually solve things more efficiently. So in the cut and choose on the circuits doesn't solve the problem of selective input attack because we're checking circuits and then we're doing oblivious transfers and there's no connection between the two. Instead of that, what we're going to do now is we're going to do the cut and choose part, the checking of the circuits, together with the oblivious transfer. And so if you cheat in the oblivious transfer by trying to run a selective input attack, I'll catch you doing that as well. I'm going to combine the two things together. So what we do is we define something called cut and choose oblivious transfer. And it's worthwhile hearing about this because I believe that it will be useful in many other scenarios as well. And this will intertwine the cut and choose together with oblivious transfer. So what's the idea of cut and choose OT? I'm not going to do the general functionality that we need, but I'll do something which is more limited in order to give you an idea of what it does. So the sender doesn't have a single input, it has a vector of S pairs. And in our case, these are exactly the keys that you need for a given wire. Remember that we have on any given wire in the circuit, there are S pairs, and you're supposed to get one of those wires in each of the circuits. The receiver has a bit, meaning which key it's supposed to get on the wire, but the receiver also has a set of S/2 indices, which we'll denote by J. And the output is going to be as follows. The receiver in every pair will get either the first key or the second key, depending whether it has the 0 bit or the 1 bit, exactly like in a regular oblivious transfer. But it will also obtain both values for every index in J. So the receiver within the oblivious transfer says, okay, I have a 0 bit on this wire, so give me all of the 0 keys. But also in half of the circuits, give me both. Without actually telling the sender that it got both. I know from the functionality definition the sender doesn't know which ones the receiver got because the sender gets no output. This is an ideal functionality. This is a functionality that I'm going to define. I'm going to compute this with full simulation and I can use it exactly like you use any oblivious transfer. So the receiver, in addition to getting the single key that it's supposed to on the wire which is associated with its input, in half of the circuits it gets both wires. Can anybody already see why that helps you? What does getting both input values on a wire in a circuit mean?
That's opening of the circuit.
That's opening the circuit. So if I use the same J in all of the circuits, which I'll force the receiver to do, then it means that for that set J, it's actually opening the circuit. And for the others, it's just getting a single value. But it's doing it all at once. The opening is now no longer separate from the oblivious transfer. So if the sender tries to run a selective input attack, it's going to be caught exactly like as if it had constructed an incorrect circuit. Okay, so P1 sends the garbled circuits and commitments to its own input wires, these special commitments that we said, which are the Diffie-Hellman things. Then they run the cut and choose OT for the... Okay. The things you do. So then P1 and P2 run cut and choose oblivious transfer for the input wires of P2. And that essentially means opening the circuits. It's not completely opening the circuits because there's also P1's input wires. In this cut and choose oblivious transfer, P2 gets all of the values on its own input wires. But in order to open the entire circuit, it also needs all of the values on P1's input wire in that circuit. But if P1 gives RJ, then firstly P2 can check that it's the correct value because it has the commitment G to the RJ. But if it gets RJ, then it can compute all those keys itself because it has G to the AI0. It can raise the power of RJ, and now it has exactly P1's key on the jth wire, on the ith wire in the jth circuit. So it can compute that itself just very, very easily. And then it has all of the values on all of the input wires, and it's a full opening and can fully reconstruct the circuit. So now the circuit checks and the oblivious transfers are fully intertwined into a single operation, and any incorrect value which is used in the oblivious transfer is either used very few times, in which case it doesn't affect the majority result, so I don't care about it, or it's used many times, and then I catch the sender with very high probability. So remember that beforehand, if the sender in the previous protocol, if the sender was to use the one, to give an incorrect key on the ith wire for the one value in all of the circuits in the OTs, then it wouldn't be caught if the receiver's bit was 0. It wouldn't be caught because there's no mechanism to catch that attack. But now it will be caught because in half of the oblivious transfers, the receiver is going to get both bits irrespective of its input. So we're separating the check on the values from the input, from P2's actual input. P2's actual input. It also solving all the problems in once means that you can have actually a much cleaner proof of security because it all comes down to one thing. But how do we construct cut and choose oblivious transfer? Again, this looks like something which is expensive, which seems difficult to do because half of this, you send half of the values at random, and then half of them you get everything, and the other half you only get one. It looks complicated. Same answer, by doing things, setting things up correctly, it's not too bad. And the background is the oblivious transfer of Picard, Vinod, and Waters, which Benny mentioned this morning but didn't go through. I'm going to go through it now. We'll see how much time I have. I hope I'll get through enough of it. It's based on something called the following function, which is called the RAND function. This is actually a function which is implicit in the Naor-Pinkas oblivious transfer of 2001 that Benny showed you earlier today. And you take four values, W, X, Y, Z, and you output a pair UV, which will be W to the S, Y, T, and X to the S, Z, T, where S and T are random values. This is a transformation. The interesting thing is that if W, X, Y, and Z are a Diffie-Hellman tuple, meaning that there exists some value A, so that X equals W to the A, and Z equals Y to the A, so that's what I'm going to mean for this next couple of slides for a Diffie-Hellman tuple, X will be W to the A, and Z will be Y to the A. And if that's the case, then V, which is X to the Z, Z to the T, will be W to the AS, Y to the AT, because remember, X is W to the A and Z is Y to the A, so I just replace those. And that will exactly equal W to the S, Y to the T to the power of A. So that's exactly U, and that means that V will equal U to the power of A. So if it's a Diffie-Hellman tuple, if W, X, Y, Z is a Diffie-Hellman tuple, then this pair UV that I'm going to get is a very special pair, and V equals U to the power of A, where A is exactly the exponent of the Diffie-Hellman tuple. The idea is that actually the receiver knows A. So if it's a Diffie-Hellman tuple, because it sent that Diffie-Hellman tuple, then it knows a very special relationship between V and U. V equals U to the A. And therefore, if you're given U and V prime, where V prime equals V times M, which is an encryption essentially of M under U and V, type of sort of like an El-Gamal encryption, then you can compute the decryption. You can get M by computing V divided by U to the A. So if I send you W, X, Y, Z, and W, X, Y, Z is a Diffie-Hellman tuple where I know A, and you apply this RAND function and use that to encrypt the value M, then I can get back M. Is that clear to everybody? What happens if W, X, Y, Z is not a Diffie-Hellman tuple? Let's have a look. So X equals W to the A, and Z equals Y to the B, where A does not equal B. Let's try and see what V equals. Like before, V equals X to the S times Z to the T. That's the way it's exactly constructed. Well, that's W to the AS times Y to the BT. Let's just let Y equal W to the C. Okay, Y has some sort of, it's somehow related to W because it's a prime order group, so everything's fine. So let's just Y equal W to the C. then you get that V equals W to the AS plus CBT, whereas U equals W to the S plus CT, because that's by the definition here. We know that U equals W to the SY to the T, so that's here. So we have these two equations, and it turns out that AS plus BCT and S plus CT are actually linearly independent equations. And if they're linearly independent equations, that means that for every M, there exists an S and T so that U times V prime, U and V prime together, which is U, V times M, is appropriate. In other words, the random function, the rand function, when it's not a Diffie-Hellman tuple, actually gives you completely random values, information theoretically. The analysis that Benny showed you this morning on the Naor-Pinkas oblivious transfer can actually be described in this way. Although it's more complicated than you specifically for that protocol, but that's actually what's going on beforehand. One of them is Diffie-Hellman tuple, one of them is not a Diffie-Hellman tuple. The one for which it is a Diffie-Hellman tuple, you can obtain the value using this, and for the other one, which is not a Diffie-Hellman tuple, you know absolutely nothing about it. And that's exactly what the rand function is. So PVW works as follows. You have a pair of inputs M0, M1 for the sender and a bit sigma for the receiver. This is actually not the PVW protocol. This is a version of the PVW protocol. PVW does universal composability with a common reference string, and this is a version for the standalone model. So the receiver R sends a tuple G0, G1, H0, H1 that is not a Diffie-Hellman tuple. Okay, so H0 is G to the A, and H1 is G to the 1B, and A does not equal B. In addition, R chooses a random R and sends G to be G sigma R and H to be H sigma R, where sigma is that input bit. It's confusing until the end, so just bear with me and I'll explain why we're doing these things. And R sends G and H to S. S then computes this rand function twice. Once using G0G H0H, using G and H here and G0 H0 from here. And once using G1 and GH from here and G and H. So G1, G, H1, H. And then it sends this U0, V0 times M0, U1, V1 times M1. Now the important point is that only one of these two tuples is a Diffie-Hellman tuple. G0, GH0H or G1G, H1H. I'll explain why that is true in a second, but if you believe me for 1 second that only one of them is a Diffie-Hellman tuple. If only one of them is Diffie-Hellman tuple, then that means that in only one of them the rand function is decryptable. In the other one, it's just a completely random value, and so perfectly hides the M message. So now I just have to convince you that only one of those is a Diffie-Hellman tuple. In order to see that, recall that the original tuple G0, G1, H0, H1 is not a Diffie-Hellman tuple, because that's what R sends. We're going to have to prove that later on as well. So H0 equals G0 to the A and H1 is G1 to the B. Now that means that for every pair GH, for every pair GH, if it happens to be that G equals G0 to the C and H equals H0 to the C, then it cannot be that this equation also holds. Because if both equations held, then this would have to be a Diffie-Hellman tuple, the original tuple. But it's not. So that means that G and H can only have a common Diffie-Hellman exponent either with G0, H0 or with G1, H1, but not both of them simultaneously. That means that at least one of the M0, M1, that's another typo, one of the M0, M1 is going to be perfectly hidden. Now in terms of simulation, all you need the simulator to do is to send G0, G1, H0, H1, which is a Diffie-Hellman tuple. And if it sends it, which is a Diffie-Hellman tuple, then both of these will be Diffie-Hellman tuples and everything will be fine. Let's leave that for a second. I want to show you this because this is, I think, a nice way of doing things. What prevents R from sending a Diffie-Hellman tuple? So R can prove in zero knowledge that's not a Diffie-Hellman tuple. This is indeed an NP statement. It's an NP statement because the fact of something being a Diffie-Hellman tuple is an NP intersects co-NP. I can just give you A and B and show you the difference. So that's an NP witness. But I don't know how to do that efficiently. Now I want to prove to you that something is not a Diffie-Hellman tuple. That seems to be much, much more difficult than proving that something is a Diffie-Hellman tuple. We saw this morning that proving something is a Diffie-Hellman tuple is very, very easy. The alternative is to do something really, really simple. It's to say that, to notice that the protocol, the security of the protocol just relies on the fact that the tuple is not a Diffie-Hellman tuple. It doesn't, we don't care if the values are random or not random. All we care that it's not a Diffie-Hellman tuple. So what R can do is can send G0, G1, H0, G1, G0, G1, H0, H1, where H0 is G0 to the A and H1 is G1 to the A plus 1. Okay? That's all. That's what's going to send. And then it will just prove that, well, if you take G1 and H1 and divide it by G1, then it is a Diffie-Hellman tuple. And if G0, G1, H0, H1 divided by G1 is a Diffie-Hellman tuple, then clearly the original one is not a Diffie-Hellman tuple. Now this is really, really easy to prove. Okay, so again, it's how to set things up in a way that it's easy to prove. If I take an arbitrary non-Diffie-Hellman tuple, I don't know how to do it efficiently. Maybe it can be done. I don't know how to do it. But if I do it this way, then it can be done very, very efficiently. So how do you do the cut and choose OT? So R again chooses, now R is going to choose two tuples. I'm going to do it on two executions. For cut and choose on many, you can do the same thing. R will choose two tuples. One will be Diffie-Hellman and one will not be Diffie-Hellman. One will not be Diffie-Hellman. In the case that it is Diffie-Hellman, then what will R be able to get from the Bolivius transfer? Remember, we're doing a PVW protocol where in the beginning you sent only, R was supposed to send a non-Diffie-Hellman tuple, then could get only one value. Now we're doing two executions of the PVW protocol. In one of them, R is going to send a Diffie-Hellman tuple, and the other one is going to send a non-Diffie-Hellman tuple. In the one which it sends a Diffie-Hellman tuple, what will it get for output? It will get both values. Because if the original tuple is a Diffie-Hellman tuple, then R will be able to decrypt both of the messages. In the one which it's a non-Diffie-Hellman tuple, it won't be able to. Now R needs to prove in zero knowledge that one out of two tuples are Diffie-Hellman. How do we do that? Or of sigma protocols. Why don't you have to prove to you that 80 out of the 160 are Diffie-Hellman tuples, or are not Diffie-Hellman tuples, sorry? How do I do that? CDH, exactly. CDS, sorry, we saw that this morning. So this again can be done efficiently, proving a subset that 80 out of 160 tuples are not Diffie-Hellman. Then R and S just run the rest of PVW on these tuples. The execution for which the tuple is not DDH is a regular PVW with this transfer. You get only one value. In the other execution, R gets both values. More importantly, the sender doesn't know which one happened. Why doesn't it know which one happened? Okay, the zero knowledge definitely doesn't reveal anything because it's an OR of zero knowledge. What about the actual tuples? Why don't they reveal anything? Because the decisional Diffie-Hellman assumption says that Diffie-Hellman tuples and non-Diffie-Hellman tuples look the same. Computation indistinguishable. So the sender has no idea which one the receiver got. In one of them, the receiver gets both. In the other one, it gets only one. And you can do this also for 80 out of 160 or whatever you want to do. It's 64 out of 128. You can do all these things efficiently by setting things up correctly. One thing which I didn't mention, I will mention now, is that constants are crucial for concrete efficiency. So we saw that, we talked about 720, but in general, there are a lot of optimizations that you can do, and it's important to consider because the difference between a million exponentiations and 500,000 is very, very different in practice, and when you want to actually implement something and demonstrate that secure computation can be useful, then optimizing constants is very, very important. There are many other considerations that we could discuss. I mentioned this beforehand, exponentiations are not all equal. These are just a few highlights of things that are worthwhile thinking about when we do concrete efficiency. I mentioned that. there's these multi-exponentiation optimizations. If you don't know, computing g to the s times h to the r is actually like just 1/3 regular exponentiations. So you should count it that way. In conclusion, we can compute any function in the presence of malicious adversaries with a full simulation-based proof with reasonable efficiency. And I say reasonable because I'm not going to lie to you and say this protocol can do a circuit of 100,000 gates in less than a second, because it definitely cannot. I don't exactly know how long it is, but I'm sure that it will be at least a few minutes, if not more. In particular, the blow-up of 128 times the hour is problematic. However, if the circuit is small, and sometimes, in fact, in the last talk of today, Benny will talk about computing the median efficiently, there you need a small circuit, then this protocol will be very, very efficient for that sort of task. But if you're having large circuits, then just the fact that you have to do 128 times the hour is going to be problematic. But we're moving forward quickly, so it's worthwhile jumping on the train. The other solutions that are known all require exponentiations per gate, and that's a trade-off. So that's something sort of incomparable. Depends on the size of the circuit, what your blow-up is, what your constants are. If the circuits are very, very large, then exponentiations per gate are going to be problematic. I already mentioned that beforehand. And are there any questions? Thank you very much.